Okay, we're going to do section 12, H12E, exponential and trigonometric motion. And we're going to be referring back to this identity in your formula packet where cosine squared theta plus sine squared theta equals 1. We're going to need to remember and come back to that from time to time. So anyways, we start off with this investigation, and that we're given that the displacement vector is r cosine omega t and r sine omega t. Okay, so uh, so this funny looking W is called omega. It looks like a 3 kind of sideways. Just so you're aware, it's not really a W, but it's kind of a sideways 3. It's kind of curled up at the top. Anyways, so consider the distance of the particle from the origin t. Show that the path followed by the particle at the center of the origin states the radius. Okay, so to find the distance from the origin, we need to figure out the magnitude of the displacement of the vector. So to figure out the magnitude, we got to take the square root, and we have to take this first value and square it, and the second value and square it. Now, notice I have r, and then this cosine thing squared plus r, and the sine thing squared. So if I what I really have is I have r squared, I've got this cosine thing squared, and then I've got r squared and the sine thing squared. So I can factor out the r squared, and then I get this. And now I can use my identity that we know cosine of something squared plus sine of something squared, that's going to be equal to 1. So I'm going to replace that yellow stuff with 1. And now I can say that that the square root of r squared is just simply r. So since this is a constant value, that means the motion is a circle and the radius is r regardless of time. Notice there's no t in this final answer. So regardless of wherever I am in this displacement vector, the magnitude is always going to be r. I'm always going in a circle with this displacement vector. Okay, now write down the initial position of the particle. Okay, so the initial position happens when the time is 0. Okay, so what I'm going to do is I'm going to plug in 0 in place of time here. And now I'm going to have r cosine 0, sine cosine 0. And cosine of 0, okay, well, sine of 0 is 0, and cosine of 0 is 1. Okay, for this assignment, your mode needs to be in radian. It will later on we'll need it to be in radian. So okay, so cosine of 0 is 1. So I'm going to replace cosine of 0 with 1, and I'm going to replace sine of 0 with 0. And so if I straighten this out, simplify it, I end up with my initial position is going to be r and 0. Okay, so hence the initial coordinates is r, 0. Okay, hit pause anytime you need to, if you need more time to copy something down. Okay, so give the value of t when the particle first returns to its initial position. So it's going to go around a circle, right? So the particle is going to go back to its original position when t is equal to 2 pi over omega. Okay, that looks like a W. Omega needs to kind of curl back like that. So why is it 2 pi over omega? So if you go back to the original displacement here, if I multiply omega times 2 pi over omega, it simplifies to just 2 pi. And when I get to cosine 2 pi, I'm back where I started with. If I get sine 2 pi, I'm back where I started with. Okay, I hope that makes sense from earlier trig stuff. Okay. Find the velocity of the particle at time t. Okay, so to figure out velocity, as we learned in our last lesson from H12E, or maybe it was C, I don't remember, to figure out the velocity, we need to take the derivative of the displacement vector. Okay, so the sorry about that. The derivative of the displacement vector gives me, okay, so we have r cosine omega t dt. Okay, so we've set it up for the derivative, and the derivative of cosine is negative sine, and the derivative of sine is cosine. So I plug those in, and here is my velocity vector. Throughout this handout, I'm going to use some color coding. So when I'm talking about velocity vector, you're going to see that I'm going to highlight it in pink always. If I'm talking about displacement vector, I'm going to highlight the displacement vector in blue. Just wanted you to know my color coding for today's worksheet. Okay, show that the speed of the particle is constant and state its value. Okay, well, speed is the magnitude of the velocity. Okay, so I need to figure out the magnitude of my velocity. So, so to figure that out, I take the square root of negative r omega sine omega t squared plus r omega cosine omega t squared. Okay, and then I can see that I'm going to factor out, this is going to be r squared, and then I can factor that out because it's in both of them. And there's an omega squared that I can factor out as well. And then I'm left with this. And like our earlier identification, we notice that that is equal to 1. Okay. So now if I take the square root of r squared and omega squared, we are simply left with speed is equal to r omega. Okay, this will come back in the next page or so. Okay, hit pause anytime you need to think about this or rewind. So just, right. Okay. Show that the velocity is always perpendicular to the particle's displacement vector. Okay, so in order to be perpendicular, we learned in chapter 3, way back in chapter 3, that if the dot product is 0, or if the scalar product is 0, then it's going to be perpendicular. So, so the velocity vector and the displacement vector. So the velocity vector, if we flip the page back, our velocity vector is r cosine omega t, r sine omega t. And our velocity vector, which we found out, was r omega sine omega t and r omega cosine omega t. Okay, if we flip the pages, right? See, there's my displacement vector, there's my velocity vector. Okay. Now, how do we do the dot product? You've probably forgotten that, right? It's okay, I'm going to show you. So I'm going to take this top value times this top value, and then plus this bottom value times this bottom value. And when I do that, I end up with r times r gives me r squared, and we've got this negative here, and then we've got this omega here, and we've got cosine omega t and sine omega t. We multiply that and that together, we get the same thing. And then we're going to notice all of this is the same. Except this one's negative. So if I add them together, we end up with 0. Thus, we've proven that it's perpendicular because the dot product, or the scalar product, this is also called scalar product, the scalar product is 0. Okay. Explain what this means geometrically about the direction of the motion of the particle. Okay. So, you can read this on your own, but I'll just read it for you. And my picture, I'll explain the picture because it kind of goes along with this. Okay, so the direction of the motion is always tangential to the displacement vector. This can be illustrated by imagining an object on a string being spun in a circle and asking which direction it will go if the string broke. So the blue circle represents displacement. It represents the position of an object at time t, whatever time is. And this here, this pink line here represents my velocity vector. And we just proved right here that the displacement vector, the blue part, and our velocity vector is going to be perpendicular. Okay, if it's perpendicular, it creates a right angled tangent. Okay. Find the acceleration of the particle. Okay, so the acceleration of the particle, we have to take the derivative of our velocity vector. Okay, so here is the velocity vector, which we got from the previous page, which was highlighted in pink. And we're going to take the derivative of each of these. So the derivative of sine is cosine, and the derivative of cosine is negative sine. Okay, so once I take the derivative of those, we end up with this. Okay, and there is my acceleration vector. And for the rest of this handout, I'm going to be highlighting acceleration vectors in yellow. Okay. Question B. Show that the acceleration is always perpendicular to the velocity vector. We're going to do exactly the same process we just did here. So my acceleration, so here's my velocity vector, the pink one that was on the previous page. Here's my acceleration vector, which we just found right here. And if I do the dot product, I'm going to show that the dot product is going to give me equal to 0. So this part here times this part here is going to give me this, plus this part here times this lower part here is going to give me this. And notice this is the same, except we've got a negative. Add them together, bam, we get 0. Hit pause or rewind if you need to hear this again. Okay, next part. Let A be the acceleration velocity vector of the particle. Okay, show that the magnitude of A is equal to the magnitude of the velocity squared divided by r. Okay, so first things first. Let's find out the magnitude of A. So here's my acceleration vector. I'm going to find the magnitude of it. So I'm going to take the x component and square it, plus the y component here and square it. Okay, so then this here becomes r squared, and omega squared squared gives me omega to the 4th power. And then I've got cosine omega time squared. And the same thing here, plus sine squared sine omega t squared. Okay, and once again, using our identity, this yellow thing is going to be equal to 1. And then the square root of r squared omega to the 4th gives me r omega squared. Okay, that's the first part. The second part, what is the magnitude of the velocity vector? Okay, so magnitude on the velocity vector on the first page. Remember I said, oh, this is going to come back. Aha! See, the speed is r omega. So, I'm going to replace, so since it's the magnitude square, we've got r squared and omega squared. So therefore, I'm going to replace this with r squared and omega squared. I'm going to replace this with r omega squared. And then if I divide this right side by r, we get the same thing. Ta-da! Okay. Show that A equals KR. I'm going to show that in the homework example in just a minute, so don't you worry about that right now. Okay, conceptually, what did we just do? Okay, so vectors can be described in angular velocity, in a circular motion, by taking the derivative of the displacement vector. So if I take the derivative of the displacement vector, I'm going to get the velocity vector. Acceleration can be found if I take the derivative of the angular velocity equation. Okay? So, this is the example from the textbook. A particle has displacement r with time t, and it equals this. Okay, so remember what I said, mode radian. Okay. Find the position of the particle when t equals 0, t equals pi over 2, pi, 3 pi over 2, 2 pi. Okay. So the first thing I'm going to do is I'm going to take this equation and I'm going to replace t with 0, as you can see here. So if I, and we know that cosine, we know that sine of 0 is 0 and cosine of 0 is 1. So if cosine of 0 is 1, then I've got 10 times 1 times 1. That's going to give me 10. Sine of 0 is 0, so that bottom value is going to be 0. So this dot is right here in this picture. Okay. Then I'm just going to show all this right now. It's very difficult to, you can copy down some of this, you don't have to copy the whole thing down. But if I replace t with pi over 2 and in both places, then I'm going to get these coordinates. Okay. Same thing with here and here. And if I plot those coordinates, you're going to notice it's kind of moving around like this, and it's going to spiral in, doesn't it? So in the long term, what is the behavior that's happening? The particle is going to spiral in towards the origin right there. Okay. Like I said, you don't have to copy all this down, but if you copy some of it down, at least you can get an idea of what's happening. Okay. Find the velocity of the particle at time t. Now this is kind of what we're going to be doing in our oh, this should be r v. Right? Our velocity vector is found by taking the derivative of the displacement vector. So basically I've taken my displacement vector and put it in here, and then dt, dt. So we're going to take the derivative of this. When I take the derivative of this, now using chain rule and product rule, you get this. Okay, just take my word for it. I'm not going to ask you to bother with doing chain rule and product rule for today's lesson. Okay, so just take my word for it. Okay, find the magnitude and the direction of the velocity when time is 0. So as I said before, magnitude is, we're going to take each of these values here. Okay, before we find the magnitude, we have to plug in 0 in for our vector velocity vector, and then we end up with -5, 10. And then to figure out the magnitude, we take the square root of this squared plus this squared, and we get this. I ran out of space to do the direction, so you'll have plenty of practice of that. So let's move on to the homework problems. Actually, I'm going to make the homework problems on a second video.